Here's the answers to the third assignment that y'all did. There were some common misunderstandings and misconceptions on this, so I want to make sure we went over it. In the first problem, the first question is about the direction of the skew, and you can see here this has a tail out to the left. So when we talk about a tail, we mean something that's getting further and further away from the center, right? The center is going to be in here somewhere. And so we have stuff that's way out to the left of the center, and nothing correspondingly can go out that far to the right. So this would be skewed to the left. The tail of a distribution pulls the mean along in that same direction. So when that happens, when we have a skewed distribution, we expect that the mean is going to be pulled in that same direction from the median. And so that means the mean, in this case, the mean will be less than the median, or the median will be larger. When we have skewed data in general, we generally prefer the median as our measurement of the center. Like I said, this is somewhere around the median because it's splitting the data, half of it to the left and half of it to the right, whereas the mean would be further over to the left. So we prefer the median when we have skewed data, and especially if it's really badly skewed. The median will be a much better reflection of the middle of the data than the mean will be. And then the last one, it says the mean homework grade is 70. What percentage of the data values are 70 or above? And so we really can just count in here how big these things are. You might have to use a straight edge to go over, but this bar is 10 high, this one is 7 high, and this one is 8 high. Those are the only ones that matter because that's 70, and so this means there are 70 homework grades that are between 70 and 80. This means there are 10 homework grades between 80 and 90, and this means there are 8 homework grades between 90 and 100. So the number of homework grades that are 70 or above is going to be 7 plus 10 plus 8. So there's 25 of those total, but we're trying to figure out what the percentage of the data values. And so this of the data values means I should be dividing by the number of data values. And we're told up here that that's 42. So 22 out of 42, whatever that is, written as a percentage, is the answer to that question. So don't forget, when this is marked frequency, that means that the numbers, that the height of the bar really is the number of things in that bin. Okay, the most missed problem was 2A, and the main thing here is that you have these boxes of cereals that you're recording sugar content, and then this box plot's been made. I made it vertical just so it fit on the page better, but that might have been the thing that confused people. So when we have a box plot where you know that roughly 25% of all the data values are sitting in between these 5 lines. So the five lines are the ones that have name. So minimum, first quartile, median, third quartile, maximum. So between each of those lines is roughly 25% of all of our values. So a question like B is actually easy because it says blank percent is between 4 grams and 13 grams. Well, that's the first quartile and the third quartile. So between this line and this line, there's 25% here and 25% here, so that's 50% altogether. So 50% of the cereal is between 4 and 13 grams. The third one, C, also didn't cause too many problems. What percentage is less than 13 grams? Well, here's 13, and less is this way, right? You can see the scale over here. So if 13's here, 5's here, 0's down here. So less than 13 would be 13 or below. So that's 25%, 25%, 25% of the data is 13 or below. So that's 75% of the data. the last one, or part A, says roughly 25% contain at least blank grams. At least means so many or above. So I'm looking for the line on my graph that has 25% above it. And so that's going to be this line right here. That line has 25% above it. So the cereal that has at least 13 grams is going to account for this 25%, 13 or higher. It's going to account to 13%. So I think maybe that was misreading the word at least. I'm not really 100% sure what was being misread, but this is the right answer. And then the last problem, we're just trying to invent a data set that does something in particular. So I want the standard deviation to not be 0. And so that's pretty easy to achieve, because the only way the standard deviation of a data set can be 0 is if all the numbers are exactly the same. And that's certainly possible, but obviously that's not very, very typical. So I don't want that, but I do want the interquartile range to be 0. So if you think about it, the interquartile range is IQR, is Q3 minus Q1. And so the only way that could possibly be 0 is if Q3 and Q1 are equal. So these two numbers would have to be equal. But those numbers are going to be like here and here in the data, right? If you list these in increasing order, then 1, 2, 3, 4, 5, right? If I list them in increasing order, then the median's going to be here between those two values, and the quartiles, first quartile and third quartile. So as long as I list the data in order, that's where those quartiles have to be. And so it's easy to make those two things at the blue circles be the same. They could both be 80, say. I don't want all the data to be the same, so I'll throw in a 50 and a 60 here, and a 90 and a 95 here. But between those values, the data needs to be still not going down. And so if I have 80 for the first quartile and 80 for the third quartile, then I would have to have 80 at these values as well. So as long as that middle chunk of numbers are all the same, then you will have the interquartile range being 0. Your minimum can be whatever, your maximum can be whatever, but your quartiles and median would all be equal. So this is perfectly possible. It means we can get an IQR of 0, perfectly possible to get an IQR of 0 without all the data being the same. But the IQR being 0 means that you have a lot of data that is the same, for sure.